Hello, everyone. Welcome to the first webinar in our series of 7 different webinars on load forecasting and resource adequacy. We're so happy you could join us. Today, we're going to be providing an overview of some training and connections to state planning efforts. My colleagues Juliet Homer from Pacific Northwest National Lab, as well as Eran Schweitzer from PNNL, will be your presenters today. I'm Pete Kappers from Berkeley Lab, and I'll basically be the MC for today. If you could jump to the next slide. Just to kind of quickly acknowledge our funders here, the Department of Energy provides funding to the national labs to do a whole lot of things, but in particular, today's webinar. This is funded by a number of offices, and it's for a technical assistance program that I'll provide some more information on at the end of today's webinar. But with that, let's get started. I'm going to hand things over to my colleague, Juliet, who's going to give you a better overview of the series of webinars that is going to happen, and then begin to talk about some power system planning, kind of provide a big picture perspective. She'll hand the mic over to Eran, who's going to dig a little bit deeper in some of the models and data that you're going to see discussed in some of the later webinars. And then, like I said, we'll end up just presenting a little bit of a quick overview of the technical assistance program that funds this particular webinar series. So with that, Juliet, take it away.
Thank you, Pete. Hi, everyone. I'm happy to be with you today with my colleague, Eran Schweitzer, to provide an overview of this webinar series, and then also to provide an overview of power systems planning generally. And this will provide a nice foundation for you as you move into the other webinars in this series. Really focused on load forecasting and resource adequacy. So as Pete said, after I provide an overview of the webinar series, I'm going to, from more of a higher level perspective, talk about the different types of power systems planning, the different models that are used, and just the different types of planning that you as a state energy office staff or public utility commission staff might be involved with. And then Eran is a power systems engineer, and he's going to dig deeper into the types of models that are used in different planning processes and how they fit together. So this should provide a nice foundation for you for this series. Okay, so as Pete said, this is the first of 7 webinars that are being offered in this series. Excuse me. The second one is where we transition into forecasts. And so the second webinar is a general overview of developing forecasts. The third webinar is focused specifically on a very important and hot topic of load expansion, load growth, and developing forecasts for load growth. The fourth webinar is focused on forecasts for distributed energy resources. From there, we transition to more on resource adequacy. So the fifth webinar will be on the basics of resource adequacy analysis. And then the sixth webinar will focus on transmission and distribution system planning and provide the basics of that. And then the last webinar in the series is on the evolution of resource accreditation, which is a very important part of resource adequacy analysis. Okay, so as I said, the focus of this webinar series is on load forecasting and resource adequacy. And what we hope to do with this webinar series is empower state agency professionals with some fundamental and essential information on forecasting and RA that will be crucial for them and for you as you participate in or oversee electricity planning processes. We will be sharing key concepts, methods, techniques, and examples that you as webinar participants can use in your work in the electricity sector. In general, we really want you to be able to walk away from these webinars and be able to ask really good questions when it comes to forecasting and resource adequacy, but then also be able to understand the answers and the responses that you'd get from those questions. So the focus of today's webinar, as I said, is to provide you a foundation connecting forecasting and resource adequacy to grid planning. So the figure here on the right shows all the different elements really in the power grid. From the wholesale down to the retail, from the big generating stations to transmission systems, down to the distribution system, and ultimately to customers. And utilities throughout this whole process of generating and delivering power conduct a variety of different types of grid planning activities. And then states will engage with grid planning activities in a variety of ways. Well, forecasting is really the foundation of grid planning in a lot of ways. There are forecasts associated with the load, forecasts around generation and performance and outages of generation. The costs are really important when it comes to grid planning, and forecasting or understanding potential future costs, super important, and then the performance of the system. So resource adequacy is really having the capacity to serve load and making sure that the grid at any time and in all places throughout the grid has the capacity to serve the load. So the generating resources are the supply. Of course, the load end use customers demand is the demand that needs to be served, that utilities must serve. And then importantly, we have the transmission and distribution systems that bring that supply to load. Sometimes resource adequacy, when people talk about it, they focus in on the generation part of that. Do we have enough generation to supply customers? But it's important to really also consider the transmission capacity and the distribution capacity, or the deliverability of those resources to loads. If you're involved in grid planning, you might hear some assumptions. Utilities might say they assumed a copper plate in this analysis. And what that means is they didn't consider the generation or the transmission capacity, and just kind of assumed that if the power could be generated, it could be delivered to load, as a copper plate is a pure conductor. And so it's there's no constraints on transmission and distribution. And that can be a useful assumption in certain analyses. But we're going to talk a lot about the importance of understanding the transmission's role in resource adequacy today. Another thing we're going to talk about is understanding how the different utility planning processes interact with each other. Okay, so I'm going to now talk about the big picture of power systems planning. So I am an engineer, but I'm not a power systems engineer, and I've worked for years in the kind of more policy and regulatory space. So I'm going to provide a look at power systems planning from that perspective. And then Eran, who does more day-to-day detailed power systems engineering, will talk more about the details of models and data and how the processes fit together. So context matters when it comes to planning processes. There are a lot of different contexts that utilities operate within, and that states must consider when they think about the types of grid planning that they can be involved with. Well, what are some of the factors that influence the types of planning processes that states need to be aware of? Well, first is whether a state or a utility is vertically integrated versus restructured. So a vertically integrated utility is one that owns and is responsible for everything from generation through transmission and on to distribution. So the load serving entities, you might hear that referred to LSEs in vertically integrated states, like I said, generation, transmission, and distribution. In a restructured state, the load serving entities are mostly only responsible for distribution. So the transmission generation is handled separately. And of course, that would impact the types of planning processes that the utility would undertake, that the load serving entity would undertake, and the way that states would be involved. Another important factor is whether or not the utility is a part of an RTO or an ISO, a regional transmission organization or independent system operator. So out here in the West and in the Southeast, utilities are not part of RTOs or ISOs, and that really kind of changes the types of planning that states need to be aware of or participate in. So in RTO and ISO regions, the RTO and ISO is responsible really for the resource adequacy through a market construct. And onto the next item here, market constructs also are important. They can impact how utilities and RTOs and ISOs plan and secure energy, whether there's centralized capacity markets and that sort of thing. And then finally, whether a state requires integrated resource plans by utilities, and kind of the level of rigor in those requirements can also impact how a state would be involved in utilities planning processes. And I'll talk more about IRPs here in just a minute. All right, so at the highest level, the types of electric system planning are focused on first generation, also called resource planning, which identifies the types and location of power plants or contracted generation needed to meet future electricity demand. Then we have transmission planning, and this is identifying how that electricity is transported from where it's generated to the distribution areas. And then finally, distribution planning identifies how that electricity is delivered from the transmission system down to end use customers. So where does resource adequacy fit into this? Well, when I was first creating these slides, I was thinking of, talking about it as resource adequacy planning. And as Aron and I discussed, it's really not planning. It's more of a resource adequacy analysis that is conducted. And it's really the process of ensuring that the electric system has enough electricity generation to meet customer demand, and enough transmission capacity to deliver it at every hour of the year and throughout the entire system. So resource adequacy analysis can look at both future generation and transmission assumptions, consider a wide range of normal and extreme conditions. And then when you talk about resource adequacy, how is it measured? Well, it's often measured by the probability of an outage due to insufficient capacity. An example that is pretty common is a resource adequacy standard that says there must be less than 1 day of generation-related outages every 10 years. So sometimes you're 1 in 10, and that is a resource adequacy standard. The types of plans that may be required by public utility commissions include integrated resource plans, or IRPs. These are plans to meet the utility's future electricity demands by selecting a portfolio of resources with the best combination of expected costs and risks. And when we talk about costs and IRPs, this includes both kind of investment costs of the new capital assets that need to be constructed, but also production cost or operating costs, fuel costs, and things like that. So IRPs try to devise portfolios that will reduce investment costs and production costs. IRPs often include both generation and, to a lesser extent, transmission. And ensuring resource adequacy is a critical objective of IRPs. And the planning reserve margins are outputs of a resource adequacy analysis, and then they can be inputs to the capacity expansion modeling that happens in integrated resource plans. So distribution system plans are another type of plans that state entities will be potentially involved with. And a number of states are kind of having additional requirements for distribution system plans these days, or integrated distribution system plans, as they're sometimes called. And these lay out all those distribution system needs and identify plans for addressing those needs. Investments in the distribution system these days are over 50% of the grid investments that we're seeing. So these are large costs, and it makes sense that regulators and state energy offices are interested in understanding distribution systems planning and being involved in those dockets and proceedings. A few states are moving to integrated grid plans, which kind of combines integrated resource planning with distribution system planning, includes generation, transmission, and distribution. So that's an emerging area. And then some states have topic-specific plans, such as resilience plans, wildfire protection plans, storm protection plans, or clean energy implementation plans. Okay, so transmission planning is the landscape for transmission planning really varies a lot across the country, whether you're in an RTO or ISO area or not, or whether you're a vertically integrated utility or not. But in general, FERC has responsibility for regulating interstate transmission in the country. So FERC, in a lot of cases, takes over some of the state responsibilities when it comes to transmission. But all transmission utilities, whether they're in RTOs and ISOs or not, or transmission owning utilities and RTOs and ISOs conduct transmission planning as part of NERC requirements to meet local system reliability standards. So this is something that is going to happen on a regular basis. These utilities or RTOs, ISOs will conduct this detailed reliability studies, and these transmission planning organizations and utilities will also plan for economic needs and public policy upgrades. So FERC Order 1920 is a relatively new requirement that requires transmission planning organizations to conduct recurring regional long-term transmission planning. So in vertically integrated utility states, utilities, as I said before, will often include transmission in those integrated resource plans. Okay, so what does all this mean for states? Well, states will participate in and influence the RTO and ISO planning processes. So if their states are within an RTO or ISO, they'll be engaged in that planning process with the RTO and ISO. FERC Order 1920 actually has even more explicit roles for states when it comes to providing input on scenarios that are modeled and cost allocation. And states will acknowledge or approve transmission in integrated resource plans for states that have those. And in some cases, the states will be responsible to approve the transmission costs for cost recovery in rate cases that come before public utility commissions. Although FERC approves interstate transmission in terms of the rates and the planning, siting and permitting is almost always a state level responsibility. So that's another way that states really are involved with transmission. Okay, so this is a slide that shows kind of the different types of models that are used in electricity planning. And so I put this list together and I discussed it with my colleague Ron, and he made the comment that this is a little bit of an apples and oranges kind of a list, but I enjoy good fruit salad, and I think it's still helpful to kind of look at them all together. So I'm going to just kind of go through these briefly. We can think of these first two model types, load models and network topology models, as really data models, where the others are more analysis models. So what do we have here? Well, load models are basically a model that represents the consumption of electricity in space and time through the system. So if you think about what the load that the utility has to serve going forward, it's not just one number, it's actually a kind of a data model that shows over time throughout the system. This is the type of load that they need to plan for. So these load models are then inputs to other types of analysis models, such as capacity expansion models. And often utilities will just develop these load forecast profiles. Then we have the network topology models. This basically is a model that visualizes and maps what does the existing system look like, what are the grid components, and how are they connected. Now, these network topology models are used to analyze electricity flow, identify bottlenecks in the system, and plan expansions. This is another data model that's used by other types of analysis models, such as power flow and production cost models. We'll talk about those in a minute. So these also are often developed by utilities, potentially with consultants. They can be GIS-based models of the system. So now we move into capacity expansion models, and these are models that are used in integrated resource plans or anytime the utility is saying, what do we need to build to meet our needs going forward? So the capacity expansion models will determine the least cost mix of power generation, storage, and even demand side resources and transmission needed to meet future electricity demand and policy goals. So they can be optimization models to help understand what should the utility build that's the least cost way to meet needs. And we've got some examples of some open source or proprietary models here that are often used. Now we move into production cost models. So production cost models basically say, okay, given a certain configuration and grid system, how do they simulate the operation of that set of assets and that grid system over a relatively short period of time to determine what's the least cost dispatch of those resources to meet load at every hour, everywhere. So they kind of simulate the operation of the system and come out with the production cost. How much does it cost to actually to operate that system in terms of fuel and different resources coming on and off at different times. And so that's an important part of planning and a cost optimization as well. Then we move into power flow models. Our grid engineers here at PNL love to run these models, and they're very detailed simulations of the physics of the power system or the transmission network. And they include those dynamic events that can occur in seconds or less than seconds that can impact system stability. And so at the end of this table here, I show the different types of planning that these models are used for. And so for these power flow models, they're often used in transmission planning. Then we have distribution system analysis models. These will simulate and analyze the electric distribution system from the substation down to the customers. And they do different things to kind of identify, is the system stable? What kinds of violations or needs are there on the distribution system? And they can be used for distribution system planning. So if we have apples and oranges, this last type of model may be a bit of a banana. It's an analysis model, but a different type of an analysis model. So this is probabilistic models. And these are used to understand probabilities and uncertainties in key variables for different types of analysis. So this model results in a distribution of possible results with associated probabilities. So this is really important for generation planning, but can also be used in distribution and transmission planning. Okay, so I think this is my last slide before I hand it over to Iran. But this slide lists the data and different information that are critical to power system planning. So if you think about planners and doing different types of planning, what kinds of data and information are important? Well, first, really understanding what happened in the past, historical information, super important. What was the demand in the past? What was the generator capacity? How did the generators perform? What did their outage look like? What were their fuel costs and O&M costs? What did the weather look like in the past and resource availability? And then what's the asset age and condition? So looking back is an important way, of course, to plan for the future. In addition to that, there's information on policy goals. Does the state have goals around renewable portfolio standards or battery storage? And then what are the resource adequacy objectives? Very important. And then forecasting and looking forward, really important as we move into forecasting, planning, and resource adequacy, understanding what is the demand going to do going forward of the load, what types of generator capacity do we have, what are the retirements of generators, what's the outages, performance, and cost, what do we expect for fuel prices, really important, weather, resource availability, and then new generation cost and performance and siting. And then when it comes to infrastructure options, things like supply chain issues and availability really feed into planning. What are the costs of building and operating the assets, and what are capabilities? So when it comes to particularly integrated resource planning, all of this information is brought together and results in a statement of, okay, this is the total revenue requirement that the utility needs to collect in order to expand the system, operate the system going forward. And that's often used as a metric in integrated resource planning. And then you can look at, well, what are the customer rate impacts from that? And then what is the overall risk profile? So that's kind of from a big picture, some of the data information and outputs from system planning. All right, so with that, I'm going to stop sharing, and Aran Schweitzer, my colleague, is going to take over the second half of the presentation.
Okay, thank you very much, Juliet. So we're going to be digging, as we were talking about, a little bit more into the models and the data. And before we get started, I just want to say that the objective here is not to become an expert in the next 15 minutes in all of these, but to start to understand how the decisions about what we're modeling and how we're modeling it lead to different requirements, what it does and doesn't make sense to do in different kinds of model settings, so that as you're presented with different information and different analyses, different results, you start to have a intuition about what are the important questions to ask. So with that, we have, as Juliet mentioned, several different kind of processes, and the important thing is to note that these inform one another. So the outputs, which I have here in orange, from each process feed into the others. Now, these are all happening on a cyclical timeline. So the starting point, the way that I laid this out here, is somewhat arbitrary. I happen to place resource adequacy in the middle because that's kind of the focus of this webinar series, but you could reorganize this however you would like. And so the idea is that we have, for example, our transmission planning. It is ingesting a load forecast. It is ingesting a future resource portfolio from some resource planning process that happened previously. And through that, it is generating some transfer constraints that it is observing in the system, as well as potential solutions for that. Those are then fed into both the resource adequacy evaluation as well as the resource planning for that future cycle. And so you can see how these are all very much intertwined, but there is a time separation between them. We're going to now look at what makes up each one of these processes. So each one of them is made up of some representation of the system. That's what we're calling the system model and data types. Some representation of components within that system. These are the component models and data types. And they bring these all together in some sort of a solution method. Now, I just represented it this way, but actually, the way that this sort of the rationale for this sort of goes in the opposite direction. Each process adopts a different solution method because it has different aims. So for example, resource adequacy is really trying to get at probabilistic measures of unserved energy. And so it is going to have a probabilistic type of approach to its solution. And because you adopt this particular kind of solution method, those induce different model and data requirements to execute on those methodologies. And in the next few slides, we're going to go through each one of these categories, the systems, the components, and the solutions. So these become less abstract and hopefully start to make a little bit more sense as normal things that you've probably seen in various different modeling discussions. We can break down system models and data types, roughly speaking, into three general categories as I have laid out here. We're going to start on the left, and we have these what are often referred to as pipe and bubble models. In these, you have these pipes or bubbles, hence the name, that aggregate load and generation within them, and then connect between these areas with pipes. These kind of models have little or no representation of the underlying physics of the system. And these are the kind of models that you see often used for policy evaluations. This is your classic IRP resource planning type of model. When we get over this dotted line over here, we start to move into the engineering type of model. So the next one we have here is a bus branch model. This is the workhorse of engineering analysis, like these power flow tools or some production cost tools. In this case, we're placing load and generation at electrical buses, and we're modeling the connection between those as branches with some sort of impedance. So we are capturing some representation of the underlying physics. Now, finally, we have what are also known as node breaker models, and they're very similar, except that they're actually representing the placement of individual switches in the system. This allows you to actually model reconfiguration, and it does become important for some contingency analysis. For example, there are some models of how switches malfunction or how you can separate the system in different sort of situations. So we talked about the system, now the components that go inside of it. And those components can take on very different kinds of styles. So we have static or snapshot type of data. So this is going to be a single value. So if you're thinking about your snapshot power flow model, this is going to be a single generation set point or a single load set point. You could instead have time series, which means that you're giving multiple values at some sort of time resolution. For example, you frequently see hourly resources, loads, etc. So this is an example from the CAISO Outlook, and you can feed that into different kinds of models. We also see dynamic data, and this is different from the time series data in that the model itself evolves the values through either differential or difference equations through the simulation. So in terms of differential type of data, that's your classic dynamic system. So you see this kind of block diagram over here of a turbine or a generator motor models. But dynamic data is also difference, which is something like the ramp rates or the charging rates that you see in more production cost model type of formulation. So dynamic does not need to be that very, very quick time studies. It can also be these slower dynamics in terms of discrete time. Finally, and relevant to resource adequacy, we have probabilistic models, and you can attach those on top of either static or time series data, and you're basically placing a distribution. Here you hear talk about these different like percentiles, so P10 or P90, load forecasts or scenarios. And then our last piece are the solution methods. And we have two general ones. One is our optimization models, and I'm highlighting deterministic because of what I'll get to at the end of this slide. So in an optimization model, we have some sort of a cost function that is associated with variables. This can be capital cost of building something. It can be operational costs or fuel costs. And we're trying to solve a underdetermined problem to find an optimal solution. On the other hand, we have simulation models, also in the deterministic sense, and these are solving a set of equations. So this is a perfectly determined system, and we set up the equations and we solve for the solution. Now, both of these can be cast in the frame of probabilistic or stochastic. And one way to think about it is that we're essentially, we have that probabilistic data, component data. And so we're able to sample from that data. We might be sampling load, generation forced outages, etc. And then with each sample, we can rerun one of these methods over here. So let's start to look at a few different examples. Here we have load models. So this is an example from the Northwest Power Conservation Council's 9th hour plan of demand forecast. And you see that we have two different types of data here. On the one hand, we have a static or snapshot peak load. So at each year, there's a single value given for that year. Now, there's a little bit of probabilistic here through various scenarios as well. On the right-hand side, we have time series or hourly load. So you see that for various years, there is a value for each hour of the year. So 8760 hours per year. And in fact, you can see here that there is a particular scenario called out. So there's a little bit even of a probabilistic through scenario analysis dimension to this that is not shown in this slide. We're now going to try to start to map these components, so the system model, the component models, the solution models, into the processes that we discussed at the very beginning. So let's look at resource adequacy. Our objective is that we want to create some sort of reserve margin and capacity certification, which is then fed, if you recall from the first slide, into the resource planning process. The system model that we generally adopt here is a pipe and bubble at a regional level. So each region is represented by its own pipe. And that is because we're going to, at the solution method over here, be running this probabilistic analysis that is often based on some sort of optimization. And so we're going to be sampling from these hourly time series loads or generation through this Monte Carlo approach to be able to generate the probabilistic results. There may be some time difference resource constraints on ramp rates. That depends a little bit on the type of specific resource adequacy model. And I just want to point out here that the idea is that we can quickly generate very large data sets if we're considering different variations on input. So for example, different weather years, different load growth scenarios like we were talking about in the previous slides. Specifically to RA, we are looking at different kinds of reliability metrics that it's worthwhile to take a beat to discuss. So the industry standard is a loss of load expectation, and there are different variations on that theme. So the one that we frequently hear is that the system should be able to withstand up to 1 day with any amount of unserved load in 10 years. Right? And so that would be a loss of load day. As you can see here, there are different kinds. You can have a loss of load hours, which is the expected count of event hours per period, or you can have a loss of load frequency, which is the expected count of events, right? When events may last more or less than an hour. And so this plot over here is attempting to place these on these various axes. We have the frequency axis, the magnitude axis, which is where the expected unserved energy is living, and the duration. And by combining some of these metrics, for example, taking the loss of load hours divided by the loss of load frequency, we can start to get a little bit more information. For example, if we take the expected unserved energy divided by the loss of load days, we have information along all three axes. The key last takeaway here is that we do this probabilistic analysis in resource adequacy, and it is then translated to a deterministic quantity, namely the reserve margin that is fed into the resource planning process. And that resource planning process is run using a capacity expansion type model. So these models are trying to explore investment decisions over years to decades and figure out what is it that we need to build and how much. When do we need to build this? Where do we want to build this? And so the input data that you're seeing are the load forecasts, those reserves margins that we just discussed, as well as capacity credits that are derating certain technologies based on how well they can address serving load at critical times of need, as well as some transfer constraints coming from transmission planning. And they're trying to come up with that future portfolio. Given all of those things that it's trying to solve, there are some trade-offs. We typically model these as pipe and bubble system models, right? So we're not really considering too much of the physics. And the component data is like a semi-time series. So we're going to pick just a few hours out of the 8760 rather than the whole time. The solution method is an optimization, and we may even see some scenario analysis brought into that. An example over here is PacifiCorp's 2025 IRP. And so on the left, you can see that pipe and bubble model, right? We have different pipes in different areas. You can see the generation and load and different contracts that they have modeled within each bubble. And then there are these paths that indicate the movement of potential energy between these bubbles. And on the right, you see the outcome of this kind of a process, which is the selected resource portfolio evolving over time. And you can see the various different technologies that make it up. Another model that you hear a lot about and that shows up in different places are production cost model. Juliet mentioned it as well. And the objective of production cost models are to operate systems at a minimum cost. And now we can construct them in very different way. So we have ones that have a system model that is pipe and bubble, and that is the underlying engine for a lot of these RA tools, like VM, for example. We also have production cost models that have a system model that's more of the bus branch, and those are what we would use, for example, for the economic evaluation of proposed transmission projects. So when we're trying to do the cost benefit analysis, it's a bus branch type of production cost model that will be used. The component data that goes into these are generally time series, frequently hourly load and generation inputs. You may see a distribution, for example, forced outage rates if you're doing some Monte Carlo around that, or different load profiles, etc. Again, if you were thinking about the RA, as well as some time difference constraints like ramp rates, etc. And this is by definition an optimization. And to point out here, right, we use production cost models both in resource adequacy, as mentioned here, the pipe and bubble as well as in transmission planning, where it is more of that bus branch model. As an example of both of these, on the left-hand side, you see the MISO loss of load expectation model. So it's clearly a pipe and bubble type system. And you can see on the bottom here that probabilistic evaluation of loss of load risk broken down by hour and year and season. On the right-hand side, you can see results from a study that PNNL did that concluded at the very beginning of this year. And here we have a more detailed transmission model. So we're seeing actual transmission lines and actual generation at specific points in space. And we can therefore capture the flow on individual lines. These are sorted in time in order to be more visually clear. But you have actually 8760 values for each realization. Finally, the last planning process that we had in that first slide is the transmission planning process. And the objective of this process is to integrate resources and reliably and economically. Now, we use two main models here. We have a bus branch model, and we have an example here from two examples actually from the CAISO transmission plan. So over here, you can see there are the various buses, and we can see the branches that connect them. Here's a transformer, transmission line, etc. We also have node breaker models. So this is an example here. And again, the main difference is that we're actually capturing the internal substation configuration. And this becomes important for understanding certain types of operations. The component models are frequently static. If we're doing basically like power flow solve snapshots, we also then have dynamic simulations. These are going to be more of the differential equation type of dynamic models. And we also see some time series, as mentioned previously, for production cost models when we're doing that cost benefit analysis. The solution methods are predominantly simulation. The workhorse, as I mentioned earlier, are power flow tools, and they're attempting to capture system behavior. So these are your power flow studies, contingency studies, dynamic studies. And again, we have some optimization to evaluate economic benefits. One key thing to note is that currently RA outputs, right? So those reserve margins and the capacity credits are not really reflected as inputs into the transmission planning process. And that brings us to one current topic of debate that I wanted to make sure you're at least aware of, which is how to account for the RA value of transmission. So there's currently a time lag between transmission and resource portions of the planning. So our transmission is over here, our resource planning portions are the resource planning is resource adequacy, and these links over here that connect them, there is a time lag. It's an annual or a biannual cycle. There means that the transmission inputs to resource adequacy are fixed. The resource inputs are largely fixed. MISO has recently introduced a calibration loop, so there's sometimes a little bit of movement there. There is currently no straightforward process to evaluate the RA benefit provided by new transmission. This is important to access new and different resources. So certain RA benefits of transmission that you already added can be captured by essentially reducing your reserve margin. But if the RA benefit is going to be in getting access to new and different resources, so changing your plans over here, that is currently not a straightforward process. As you can kind of tell in this figure, this requires really coupling all three processes together. Finally, to summarize, I tried to put some of these things on a few different resolutions. We've talked about spatial resolutions, we've talked about temporal resolutions, we've talked about different scenarios. And the core challenge of linking these processes is reconciling these very different scales in time, space, and potential futures. So just to sort of wrap this up, we have our capacity expansion models. These are like the IRP type processes. They'll evaluate some scenarios, but they're operating at a fairly core spatial resolution of a region. And they are sort of sampling in time. Then you have your resource adequacy that is similarly coarse regions, but it expands on the scenarios, right? Because it's now sampling multiple scenarios and multiple realizations because of those distributions. We go to our production cost models. They'll frequently shift down to just a single scenario, but they'll greatly expand the spatial resolution to individual substations or buses. We move further to contingency analysis. They're definitely doing just a single scenario or one or two at most, but they're operating on a single snapshot in time. So very focused, but on a few time instances and at a very fine spatial resolution. And finally, we get even to like transient models that are at a very small time resolution, but have are only considering very few different operating conditions. And with that, I'll hand it back to Juliet.
Great, thank you, Eran. All right, so we've heard a lot today. In the quick summary, utility planning processes may vary by state based on region or organizational construct. Load forecasting, critical for all three types of planning: generation, resource transmission, and distribution. Resource adequacy analysis is the process of making sure you can serve load everywhere all the time under different conditions. And as Eran described, the different plans and planning processes really do feed into and inform one another. The planning processes and underlying models will operate at different time and spatial granularity, which can necessitate different assumptions and can complicate coordination, but it's just important to be aware of that. And then the degree to which transmission and resource adequacy planning interact impacts the type of solutions that can be chosen to address resource adequacy. And this is still an active area of debate and innovation. So you'll learn a lot more about forecasting and resource adequacy in the later webinars of this series, but we hope this provided a good foundation for you. So Pete, back to you.
Thanks, Juliet. Thanks, Ron. Yeah, so just to close things out, want to let you all know out there in Webland that we do, labs through DOE funding, do provide technical assistance to state energy offices and state regulatory agencies. It comes in 3 different forms. First and foremost, 4 hours, kind of, hey, Eran, I got a quick question about some of those models you talked about. You know, Juliet, same thing, right? Just quick kind of answer, Q&A, maybe connect you with some resources that we've got available. It's a very simple intake form to get this type of support. Next up, we have what we call Expert Match. This provides up to 100 hours of access to people like Eran and Juliet for potentially more detailed issues. You know, you'd like some help reviewing a particular planning filing, you know, an IRP, something like that. You know, this might be an opportunity to take advantage of one of these 100-hour requests. Same intake form, you know, name, the organization that you're with, and then a couple sentences of what you're looking for. Within a week, you know, we'll get back to you and let you know if we can help you and move on from there. Last but not least are what we call our deep dives. These are really robust technical assistance activities. They typically are including a team of SME, subject matter experts, may do a lot of comprehensive modeling that the tools have, that the labs have available. Eran and Juliet talked a little bit about some of those, you know, capabilities of the labs. This is really something we have offered in the past and really hoping to do so in the future, but very much contingent on federal funding. And so keep a lookout on the website, that's statetaprogram.lbl.gov, or use the QR code in the lower left-hand side. Keep a lookout for that deep dive to be open. It is an application-based opportunity, unlike sort of these simple intake forms. But even there, the application should not take a ton of time to put together. So we hope to make that available in the months to come, but again, is really contingent on federal funding. And so with that, Want to thank you all for listening in today. Want to thank Aran and Juliet for this great presentation. And please do consider joining us for any of the upcoming webinars you saw listed, Juliet talked about, or access the recordings on the website where you found this one. And with that, thanks for your time, everyone. Take care.
Bye, thanks.